In this video, we'll look at how to do our phase change calculations. So if we remember our phase changes, that's when we're looking at our heating or cooling curves. Here, I show you guys a cooling curve. And we know it's a cooling curve because we start at a high temperature and we gradually cool our substance down. So here our temperature starts at 130 degrees and our water is in the gas phase. So when we're cooling from the gas phase down to the liquid phase, the molecules are starting to slow down. They're starting to lose their kinetic energy. And so this is what we call stage 1. When we're in the gas phase and it's cooling down from just pure gas phase till we hit its condensation point or boiling point. And to calculate the amount of heat that gets lost during that phase, we look at our equation here for Q equals the mass of the gas times the specific heat of the gas times the change in temperature. So that change in temperature would be from 130 down to 100, so it'd be 30. We'd look up what the specific heat of water in the gas phase is, and then we'd be told what the mass of the gas is. And that'll give us what the heat loss during the 130 to 100 degree changes. The second stage here, you can see it stays flat. We don't actually change temperature. But instead, what's happening is we're going from the gas phase to the liquid phase. So what's happening is our molecules are in the gas phase here, and then they start to condense down till they turn into a liquid. So once they turn into liquid, remember that's when we have a lot of intermolecular forces that hold the liquid together. And since it's not an actual temperature change, it's a change in phase. Instead, we're going to use Q equals the number of moles times the delta H times the enthalpy of the vapor. And in our case here, delta H is negative because we're cooling it down. We're going from gas to the liquid. If we're going from liquid to gas, it would be positive. And then once all of the molecules go from the liquid to gas phase, so at this point, they're all liquid. Then once they're all liquid, we can continue to cool down the liquid from 100 degrees all the way down to 0 degrees when it freezes. This is stage 3, when our liquid starts to cool. So stage 3, when our liquid cools, the heat loss is again the mass times specific heat of water as a liquid now times the change in temperature. That'd be going from 100 down to 0. So all of that would be our Q3 here when we're going from the boiling point down to the freezing point. Freezing point. And then once we hit the freezing point, our molecules are going to start to switch their phase. They're going to start to go from the liquid phase to the solid phase. And this happens in stage 4 of our graph here. Stage 2 is going from gas to liquid. Stage 4 now we're going from liquid to solid. And for that, our heat equals the number of moles times the delta H of fusion. Remember, fusion is the same thing as freezing. And again, it's a negative sign because we're going from liquid to solid. If we're going from solid to liquid, so the opposite process, we'd switch the sign and have the opposite sign. And then finally, once it's all solid, we can continue to cool down that solid. And so cooling down that solid would give us our Q5, or Q equals the mass times the specific heat of water as a solid times the temperature change. So that would be our temperature change of minus 40 minus 0. And so that would be stage 5. So you can see the odd number stages, 1, 3, and 5, we're actually cooling the temperature of the substance down. So that's why we use the Q equals the mass times specific heat times temperature change. For stage 2 and 4, we're switching phases. Since we're switching phases, we're going to look at the enthalpy. And that's why it's the number of moles times the delta H. Putting things together and practicing here, let's say from the data below, we want to calculate the total heat in joules needed to convert 0.333 moles of gaseous ethanol from 300 degrees Celsius down to 25 degrees Celsius. When you see a problem like this, first thing you should think, what's actually happening? What phases or what stages am I going through? Are you going to go through all 5 stages or maybe just a couple of them? So if we figure out the stages, we're starting at a gas phase. And our gas starts to cool down. So if our temperature here, that starts at 300 degrees. So if we start at 300 degrees, we're going to start cooling down till we get to 78.5 degrees. Because that 78.5 is the boiling point. So that's at the boiling point when we're going to go between gas to liquid. So then now we've gone through stage 1. Stage 2, we're going from the gas phase to the liquid phase. And remember, when we're going between phases, the temperature doesn't actually change. And that's because the boiling point doesn't change. The boiling point of ethanol is going to be 78.5 degrees at 1 atmosphere. It's not going to start boiling at a lower temperature. It's just going to complete that phase change first. And once it completes that phase change from 78 degrees down to 25, so that means we have another temperature drop, which means now we're in stage 3. And then notice how the question doesn't say anything else about it being a solid. So we don't have to worry about stage 4 or 5. Which means our total heat, we just have to calculate Q1, 2, and 3. So remember, Q1 is our stage 1. So that's the mass times the specific heat in the gas phase times the change in temperature. So that's going to equal my mass, which means I'm going to have to convert that 0.333 moles of ethanol into grams. So 0.333 moles of ethanol, which is C2H6O. So our ethanol there has a molar mass of 46.07 grams per mole. And that gives us a mass of 15.3 grams of ethanol. So that means when I use my equation, mass times specific heat of water in the gas phase times my change in temperature, the end there is going to be that 15.3 grams. So I have my 15.3 grams specific, oops, not water, ethanol. So my specific heat for the gas phase is 1.43 joules per gram degree Celsius. So I have 1.43 joules per gram degree Celsius. And my change in temperature, I went from 300 degrees down to 78.5. So the T final, 78.5 minus T initial. So when I plug all that in for Q1, I get a negative 4,846 joules. I'll worry about sig figs at the end. So then next we go to Q2. Q2, remember that's stage 2. Stage 2 is the number of moles times the delta H. So that means my number of moles is that 0.333 moles of ethanol times the delta H for vaporization. So that's 40.5 kilojoules per mole. I'm going to want to convert this from kilojoules into joules because the answer tells me I want to be in joules. And it gets a negative sign because we're losing that heat. So that means we have 0.33 times that negative 40,500. And so this gives us a Q2 of negative 13,486.5 joules. And so then we do our final one, stage 3. So in stage 3, Q equals, again, the mass times specific heat in the liquid phase times the temperature change. So our mass, 15.3 grams. Our specific heat now is 2.45. joules per gram degree Celsius. And our temperature change, we're going from that boiling point, that's 78.5, down to 25. So T final is 25, T initial is 78.5. Once I plug all that in, I end up with negative 2,005 joules. And so now Q total equals Q1 plus Q2 plus Q3. So we're just adding them all up at this point, which would be that negative 4,846 plus that negative 13,486.5 plus that negative 2,005, which doing this gives us a total of negative 20,337.5 joules. Or incorrect sig figs, negative 2.03 times 10 to the 4th joules. So we can see in our answer, it's a pretty good amount of energy that gets lost. Pretty good amount of energy is given off going through this transition. And it makes sense that the energy is given off during the transition because we're going from a warmer temperature down to a lower one. So our system is having to give out that energy and get rid of it. And so remember, with any problems involving heating or cooling curves, it's best to draw your curve out like this first, so you know which stages you're going through. If you know which stages you're going through, then you're just adding up all the different heats for each stage at the end. It makes it easier to break it down into pieces that way. Which means now you guys should be able to calculate the heat for your cooling or heating curves. And remember, heating curves, you're just going through the opposite process. So you're starting at the solid and working your way up. So our heating curve would look like the mirror image of the cooling curve.